Okay, thank you. I'm sorry that I couldn't be with you. I, of course, wanted to make the journey. As I'm sure you understand, it's a little bit challenging in northern Israel at the moment, and it made the trip to Geneva a challenge that I couldn't overcome, unfortunately. So I will be doing this presentation remotely. Following the introduction, let me just say a little bit about myself. So I'm Nir Kahn. I'm a vehicle designer. I was actually I led vehicle design at Plasan for the last 22 years and have very recently gone independent. So I'm a designer rather than an engineer. It's an important distinction. But my experience overwhelmingly is in armored vehicles through the experience which I've gained over the last 20 to 25 years, designing really quite a lot of armored vehicles for various markets around the world, of the civilian, paramilitary, military, police, working together with vehicle OEMs, working directly with end users and with customers on a lot of vehicles all around the world. So this is the experience which I'm bringing with me here. I said that I'm a designer rather than an engineer. So I think it's important to put some emphasis on what exactly design is bringing. What is the purpose of design? So you can see on screen here, I always see design as being something which is intended to add value. Design that brings and adds value to a product. And of course, it needs to do that in a way that is not adding excessive cost. So it's really about improving the value for money, improving the value proposition of the product. And when it comes to armored vehicles, that means creating a better vehicle for the user. It means saving weight out of the vehicle, and to do that efficiently and cost effectively. Armored vehicle design is much more than just adding armored materials to a vehicle. To really ensure that the vehicle is efficient and lightweight and well protected, it needs a much deeper integration of the survivability of everything that's related to protecting the people inside, and to really design that into the vehicle. And this is how you get synergies of weight saving and armor optimization, because weight that can be saved through design rather than just through materials can actually also save cost through materials. It can allow for less expensive materials to be used because that weight has been saved on the base level through the design of the vehicle. And this is true whether you're starting with a clean sheet, which we rarely are, or whether you are starting with an existing vehicle, whether it's a Toyota Land Cruiser or whatever that vehicle might be, and yes, adding armor to that vehicle. But there are a lot of things that can be done in terms of the geometry, the positioning of the armor materials in that vehicle, which can save weight, can save costs, and can optimize the protection of the vehicle. So designing for lightweight is not just about materials. I'm often asked, what's the lightest armor? Is it Kevlar? Is it a ceramic composite? Is it some new metal? Is it some new composite material which hasn't yet been invented? Well, the lightest armor is the square meter that you can avoid putting onto the vehicle. If you can design that vehicle and design that armor system so that there is less surface area, then yes, you have saved weight and you've saved cost and you've done it together. But it's actually a little bit more complicated than that. It's not just a question of minimizing the surface area. It's a question of really understanding how the armor angles affect the armor solution and where you're putting those different materials in the vehicle and how they interact with each other. So yes, it's kilograms per square meter in terms of the armor material multiplied by the number of square meters that you have in the vehicle. And as long as either of those is lower, then you're saving weight in the vehicle. But the interaction between them is actually a lot more complicated. So let's look at one example, a relatively simple example, but a counterintuitive one about how geometry can save weight out of vehicle. This is a front view of a generic armored vehicle you've got your people sitting inside it, and the simplest possible shape that you can create your armor around those people is a square box with 90-degree corners, as you're seeing up in the top here. Now, if you want to take weight out of that, take surface area out of that, it's fairly obvious that you can cut the corners off and take surface area out in a place where the internal volume is not particularly important, around the further away from the heads like that. Here you can see a nice simple chamfered roof edge. Any kid at school will tell you if you cut those corners off at 45 degrees, that's the way that you're going to take the most surface area out. But the thing is, and this is where it gets counterintuitive, this geometry with 45 degrees cut out of the corners is actually heavier than the one that has 90-degree corners. Now, how can that possibly be? The surface area is lower. How is the vehicle ending up heavier? And this is why it's so important to understand what the test protocol is going to be. How is the vehicle being tested, against what threats and at what angles? Because the armor is not the same armor all over the vehicle, and stopping the same threats all over the vehicle. Every testing protocol, and they're all different, has their particular nuances. But one thing that's quite common is that there is an angle of elevation. The vehicle is expected to be able to stop any given threat at a horizontal plus X degrees, and it's normally around 30 degrees. Again, it depends very much on the testing protocol. But let's take that example of 0 plus 30-degree elevation. So what does that mean? Your side armor, the most critical threat is not the elevated threat. The most critical threat is the horizontal threat, where it's hitting the side surface at 90 degrees, what's known as 0-degree NATO. Perpendicular threat. That armor needs to stop that threat from the horizontal angle. And any elevation is actually just making it easier. So that's what's defining that side protection. On the roof, it's the opposite. On the roof, the horizontal threat is barely scratching the paint off the roof. It's the elevation that matters. So if the maximum elevation is 30 degrees, then the threat is hitting the roof at 60 degrees down from perpendicular, and that's what defines what the material solution is on the roof. So the material on the roof is lighter than the material on the side. I think this, to anybody with any familiarity with armored vehicles, will be familiar with this. What does that mean? What happens on those roof corners and those chamfered edges? That 0 plus 30, the horizontal threat, is not the most significant threat. Like on the roof, the most significant threat is the raised elevation. And the thing is that if you've cut those roof corners off at 45 degrees, the elevated threat at 30 degrees is near as makes no difference perpendicular to that chamfered edge. It's 15 degrees off a straight hit at that chamfered edge. So what have you actually done with this geometry? In the real world, that chamfered edge is probably very nearly the same material as the side. Might be slightly lighter, but it's not very much lighter than the side. It's certainly a lot heavier than the roof. So what you've actually done here is increase the surface area of the heavier armor from the side and decrease the surface area of the lighter armor on the roof, which is why this geometry, despite having less surface area overall, is actually heavier than just the straightforward 90-degree edges. Now, does this mean that there's no point trying to cut the corners, literally cut the corners to save weight out? Well, no, it doesn't mean that at all. But it does mean that when you do that, you need to be very aware of what the testing protocol is going to be, how the vehicle is going to be tested and at what angles, to ensure that you cut the corners with angles that are actually going to be taking weight out of the vehicle and not only taking surface area out of the vehicle. So let's look at the next slide with no angles on it just yet. This is also obviously less surface area than the 90-degree edges. This has been cut here at about 25 degrees. Here, if you cut at 25 degrees, you look at the next slide, So yes, you've not made any difference to the armor on the side panels or the armor on the roof, but these side margins now, these chamfered edges, can be lighter, quite a bit lighter than the side panel of the vehicle. They're still a little bit heavier than the roof, but they are a lot lighter than the side panel of the vehicle. And here, overall, through not just through the geometry and through the material choice, but overall, this is now saving weight. So this is now with, in this case, 25-degree chamfered edges, is saving weight compared to the 90-degree corners. Now, I'm just giving this as one example because it's a fairly easy to illustrate, almost a two-dimensional approach, where you can see and understand how sometimes it's counterintuitive, and how sometimes less surface area is not necessarily less weight on the vehicle. But there are a lot of areas on the vehicle where the interplay between the factors is actually much more complicated than this. Look at the next slide, looking at windscreen angles. Now, again, if you're starting with a finished vehicle design, and you have no choice over what that windscreen angle is, and all you can do is decide how thick the glass needs to be, then so be it. But often when you have the opportunity to play around with the geometry a little bit, it can be a very good way to save weight out of the vehicle, to optimize these kind of areas of the vehicle. But it's a very complex trade-off of factors. Starting off with the viewing angles. Armored glass, ballistic glass, is heavier than opaque armor at the same threat. So on a base level, we need to reduce as much as possible the area of the transparent armor. But of course, that's getting traded off against the viewing angles and the ergonomics of the people inside the vehicle, especially of the driver, but also of the other users in the vehicle and what they can see out of the vehicle. Obviously, any idiot can save weight by making the windows smaller. The real challenge is to really optimize the glass size and the glass shape, to give maximum viewing angles exactly where it's needed, and to minimize the weight. But the things you need to account for this are the viewing angles, refraction of the glass. The more that you lay down glass, the more problematic some of the refraction can be through the thick glass. Head swing, as you can see on the slide with the occupant here, you don't want to bring the glass too close to the driver's head or to any of the occupants' heads. Generally speaking, a shallower windscreen angle actually means a larger windscreen. Look closely at the image here. The more the window lies down, the longer the glass has to be in order to give the same viewing angle for the driver or for the occupants inside the vehicle. So laying the glass down actually makes the glass larger and adds weight. That gets traded off against the fact that the roof gets shorter. The more the windscreen is lying down, the roof is getting shorter. But as we saw on the previous slides, the roof is not the heaviest armor. So we're reducing surface area of probably the lightest armor in the vehicle, while adding surface area to the windscreen, which is probably the heaviest armor in the vehicle. So you're trading off the larger windscreen against that shorter roof length. But the other factor is the three-dimensional factor. The more the windscreen lies down, you're also saving weight from the side glass and from the side panels. And this is the complex interaction to achieve, to establish for any given vehicle, for any given threat level, for any given testing protocol, what's the optimal windscreen angle? And there's no one answer. You don't expect the next slide to be a magic number with a big circle around it. These are issues that need to be dealt with on a case-by-case basis, or on a vehicle-by-vehicle basis. But overall, this is all about user-centric design. It's about putting the occupants, especially the driver, but also the other occupants, front and center in the design process, and to really design the system around them. You see on the screen here an example of a particularly advanced example of a vehicle where we really did have a clean sheet of paper. and started with the packaging of the vehicle. What's the optimal packaging around 4 occupants inside a vehicle, where each of them has a job to do? Maximizing the viewing angles, minimizing the surface area, but not just, minimizing the heavier of the surface area, and maximizing the lighter of the surface area. And to do this, it really needs a familiarity with the various ergonomic standards. And those are mostly MIL standards, but there are also civilian standards in there, and commercial vehicle standards. Familiarity with the ballistic testing protocol, the angles of elevation and the threats, and the various automotive regulations in terms of, again, viewing angles, mirror positions, head swing, safety zones, all these kind of issues. And to really tackle all of those things together in an integrated way to save weight. It all comes down to the same thing, saving weight. And I didn't start really by explaining why it's so important to save weight, but saving weight can, when done correctly, save cost, because it saves in materials, but it also improves the dynamics of the vehicle. It improves the handling of the vehicle and the safety of the vehicle. And I'll come on to that shortly. Now, what this comes down to is that a purpose-designed vehicle is often, certainly when it's well done, lighter and cheaper than a vehicle that was not designed for armor and then had armor added to it. A lot of these issues that I've been discussing are equally relevant for when you are adding armor into an existing vehicle. Let's say Toyota Land Cruiser or whatever that might be. The angles up in the side corners of the roof there is flexibility, and if you just lay your geometry down and then decide what the materials are, then you're probably not doing it the most efficient way. But for any purpose that's non-covert, obviously a covert vehicle needs to be a covert vehicle. It needs to look like an existing civilian vehicle that's common in that particular arena. But for any non-covert operation, whether it's policing or peacekeeping, health work, ambulances, all these kind of things, where the vehicle is not really a covert vehicle, sometimes where the presence of the vehicle is advantageous, it can be much better to actually start from the chassis and to design the armored body, rather than to add armor inside the existing soft armor. So, as I say, in terms of keeping the weight down, in terms of keeping the cost down, and designing for purpose, designing an ambulance to be an ambulance and not just a stretcher inside a pickup truck. And this can be done. There are ways of doing this at the end. So the end vehicle is a non-threatening vehicle, a civilian look vehicle. There's often this perception that there's a dichotomy between armored Land Cruisers on one side and military vehicles on the other, but there is a middle ground. I often use the example of the London taxi in Britain. The London taxi is a purpose-designed vehicle. It doesn't look like any other vehicle. It's not trying to look like a BMW X5 or a Toyota Land Cruiser. It looks like a London taxi, and everybody knows it's a London taxi. And it looks civilian and soft and designed and suited for purpose. There are plenty of applications where an armored vehicle can be treated with that same mindset of, okay, everybody knows that this is the UN, everyone knows that it's the police, everyone knows it's an ambulance. There's an expectation that the vehicle's armored. We don't need to try and pretend that it isn't one of these things. It's a high-profile vehicle, and then we can design the vehicle appropriately and design the armor into that vehicle, I say, to take out the weight, take out the cost, and design it better for purpose. And let's just move on to some final issues related to that user experience, and especially to the safety of the vehicle. Now, when I say designed for a purpose, a vehicle that's designed for a purpose is designed for the users inside it. It's not a family vehicle. It's not mum and dad and 2 kids going to Disneyland. It's a driver and probably some sort of commander. It's the users inside the vehicle, whether they're civilian users or police users or paramilitary users. And the vehicle really needs to be their office. It's their office that allows them to do their job. to do it safely, to do it well, and then to go home afterwards. If the only thing that we're worried about is the ballistic threat or the blast threat, and trying to give them somewhere safe to be into when there is an attack, well, the safest place to be is back home. They are out there doing a job. There's a reason they're in a vehicle. They have things that they need to do, and there are a lot of things that we can do as designers to improve their work environment. And one of the things is to actually make the protection invisible, so they're not constantly reminded of the fact that they're inside a protected vehicle. It needs to be like an invisible angel, not something they're making excuses for. And this comes down to weight of doors. It comes down to the field of vision. It comes down to sharp edges inside the vehicle. It comes generally, largely to the comfort and safety of the vehicle. So the penultimate slide here, looking at the at how protecting the occupants is more than just ballistics. It's more than just live fire tests and blast tests. The unfortunate truth, and I'm sure there'll be other speakers over the next couple of days who will be addressing this as well, is that a common crash is actually much more likely than a live fire event. The chances of somebody being injured or even worse, killed inside an armored vehicle are much higher from a crash event than they are from a IED or from being shot at. And there are a lot of things that we do when we armor vehicles that actually fundamentally make a crash more likely or even worse. Some of them are unavoidable. And the primary safety of an armored vehicle has been compromised by the fact that it's been armored. It's now heavier, so it is not handling as well. It's got a higher center of gravity. Accident avoidance becomes much harder with these heavier vehicles. You might have affected the field of view for the driver. The vehicle is fundamentally less stable. It always will be. We can do our best to minimize that, but the armored version will always be heavier and less stable and with less accomplished handling than the unarmored vehicle was. So you've affected the primary safety, the chance of being involved in a crash. We've also affected the secondary safety, the survivability of a crash. We've almost definitely deleted some of the airbags because of the nature of adding armor, certainly the side airbags, where they're hidden around in the trim, which is where we've now put armored materials. We've affected the crumple zones, the frontal crumple zone, which is a key one between the bumper and the occupants, which is designed by the vehicle manufacturer to absorb energy and to crush. And we've put harder materials in there and affected that ability. Also in the side of the vehicle, side impact, roof impact, all of those crush zones and crash zones that have been very carefully designed by the vehicle OEM have almost definitely been compromised in the armored vehicle. So what can we do to try and alleviate that? These are the unavoidable things, or largely unavoidable things. We can do a better job, but these are largely unavoidable things. So we can minimize the weight, of course, as I've been discussing up until now. But there are other things that we can do on the final slide here. You can see that can really improve the survivability chances of the occupant inside the vehicle. The first and most obvious one, and the one that is often, unfortunately, not taken care of properly, is just to ensure that passenger safety zones are not infringed upon. A vehicle is designed around a certain bubble around the occupants, and inside that bubble there must be no sharp edges. There must be nothing that's going to harm them in a crash incident. And often in armored vehicles, accessories, radio systems, speakers, fire extinguishers, communications, all kinds of equipment is put inside these vehicles. And often not enough care is taken to ensure that they're installed in the vehicle in a way that is not going to increase the chance of injury in a crash. And this is an area, especially where I say, as myself as a designer, where it's really a key part of the work, is to really design that the interior environment to be a safer environment, taking care, positioning all of that equipment, whether it's, I say, a speaker over the guy's head, but also securing the equipment so that it doesn't fly loose. So it doesn't fly loose in a blast event, but also so it doesn't fly loose in a regular crash event. That often involves just ensuring that there is a secure place for everything. The example I normally give is just a drinks bottle. You know, a 1.5 litre bottle of Coke. You'll often see people driving around, and there's a bottle of water or a bottle of Coke on the rear parcel shelf. And I just want to show these people what happens in a crash to that 1.5 litre of Coke that's just sitting there on the parcel shelf in the back of the vehicle. Because a 1.5 kilo projectile flying forwards at 10 or 20 G in a crash is lethal. That can be ultimately what causes a fatal injury to occupants inside the vehicle. So we've gone through all this effort with the test protocols and with the ballistic materials and the blast testing and all of this fantastic effort to protect the people inside the vehicle. And ultimately what kills them is that we didn't give them somewhere secure to put a bottle of water. And that, I say, it's just one example, but there's all of the equipment that goes inside the vehicle really needs a secure place to be. You know, if our job is to give them a vehicle to keep them safe and to take them home, then yes, they need a secure place to put the bottle of water. They need a secure place to put their portable radio, to put all of the various different bits of equipment that are inside the vehicle. Some basic stuff like softening edges, increasing the radii. You don't want any sharp edges inside the vehicle at all. And you often see those on the corners of communications racks and I say communication speakers and all this kind of thing. Laptops just bolted right in front of the occupants, so that in an accident that comes up straight into their face. All these kind of things. And then the final issue is emergency exits, and everything really that's related to locks and to door locks. Armored doors are heavy. They're not easy to lift. If you've armored a 4-door vehicle and for whatever reason it's now on its side, you can't kick the windscreen out because it's an armored windscreen. The 2 doors that it's landed on, you obviously can't open. But the 2 doors that are now up in the air are also particularly difficult to open. Those are heavy doors that you're now having to lift. Really, all armored vehicles should have an additional emergency exit, preferably a roof exit or a rear exit that's at the very least accessible from the inside, so that people can get out of the vehicle in an emergency. The more complicated issue, and again, there's no one answer here, but you need to really think things through before you define the lock mechanisms on your vehicles, is the options for an emergency crew coming to extract people from a vehicle. Now here there's a very tricky trade-off, because on the one hand you want to make sure that any emergency services that arrive at the vehicle after a crash or a blast or a live fire incident, if the people inside are not capable of getting themselves out, then the emergency crew needs to be able to get them out. But if the whole purpose of your vehicle is to secure a VIP, then the last thing you want is some big red handle on the outside that everybody knows is going to open the vehicle. And this is often a tricky trade-off to really define carefully and to define properly. How do you ensure that your doors are going to stay closed after an event, in order that nobody who you don't want to is going to be able to get in, but still allow emergency crews and emergency services to get in? And I say there's no one answer to this. It depends very much what the environment is, who are the emergency services, and how well they're equipped. But it can often help to have an emergency tool, a secure tool that you know that the emergency services in your environment has, and for them to know how to get into the vehicle, but in a way that your average bystander will not be able to. Again, it's a trade-off. it's a safety trade-off that needs to be very, very carefully considered, because there's no one easy answer to this. How to ensure that the people inside are safe, extractable, but not extractable by anybody who you would want them to be. So on that vague note of what constitutes safety, I will wrap this up. To summarize, design has a significant ability in any armored vehicle, whether it's a covert armored vehicle or whether it's a ground up clean sheet armored vehicle, to take weight out of the vehicle, to take weight out effectively and efficiently. Often there are advantages in having if not a clean sheet, at least a bespoke, tailored armored body for that vehicle. Basically, for anything that's not a real covert operation, there are some significant advantages to having a tailor-made, or at least a designed for purpose armored body. And to make sure that when you're creating your vehicles or defining your vehicles, or setting the specifications for the vehicles, to really think about safety in a holistic level, not just in terms of blast and ballistics, but in terms of crash safety, in terms of occupant safety, and in terms of the occupant environment. And so thank you very much for the opportunity to present. I apologize once again for not being able to do this in person. I hope it wasn't too far compromised. My contact details are up there on the screen, and please feel free to get in touch with me at any time. Thank you very much.
Okay, well, thanks very much, Nir, for that excellent presentation. Hopefully the technology has allowed people to enjoy the fruits of your knowledge and certainly vast experience in relation to the design. And so there's a few points that I wanted to raise, and maybe we can have a short Q&A on this. Maybe anticipate some of the questions that the participants at the CAV forum might have. And you started in relation to the role of design, which I see very much that holistic approach to the vehicle. And one of the last points that you raised, and something that certainly occurs to us as independent consultants, and something I've had to deal with in my sort of 20 years in this game, is that there is a degree of stovepiping of separate designs around the vehicle system. And you as a designer really bring this together, if you like. And so you made mentioning about, the design on the interior of the vehicle, where the communications equipment or the human dynamics issues within the vehicle, the rear cargo, and I'll talk about and ask some questions on that same time. These are all designed separately. So there is an armored designer who's gone and done his work, and then an electronics designer who's done the electrics designer, and a comms designer on his. And someone just sort of brings it together and makes sure that it fits. I think your point was very valid, that it's all got to be considered holistically about that as the design. And so my first question, and I know this has been raised before, is the design implications and issues in relation to ballistic protection, and then related to blast protection. And this comes up quite frequently, in that a number of the major users of the civilian armoured vehicles ultimately only want a ballistic protected vehicle. Some people will say, the B6, for which an up armourer will take a VR7 and maybe ERV design vehicle and make a few changes and call it B6. But ultimately the customer just wants a ballistic protected vehicle. So from your perspective as a designer, are there any sort of fundamental differences, changes, enhancements you need to make to create the blast protection aspect as against the ballistic protection aspect of a vehicle?
Well, certainly when it's a cleaner sheet, and because this really affects the packaging of the vehicle and where and how the people are sitting in the vehicle. So again, if we're up armoring use the same code word, a Toyota Land Cruiser, we're not moving the people around, and we're not changing where and how they're sitting if we're adding blast protection. We're really adding weight to add that blast protection. But when it's when you do have a slightly cleaner sheet, even starting from a commercial chassis and building up from that, the blast protection is really designed around the occupants. And one of the first things that we try to do is to move the occupants to a place which allows for more efficient blast protection. So that means moving their feet away from the wheels. It means raising the seats. It means creating some space around those people. So yes, those are fundamental things to the design. The two designs that may look quite similar, but one of them's got blast protection and one of them doesn't. If the blast protection is efficient, there really should be some quite fundamental differences between those vehicles. The one example I can actually give you, work that I did back at Plasan, is between the two versions of the Plasan Sandcat, quite a well-known vehicle that Plasan does based on a Ford chassis. The regular Sandcat has very good ballistic protection, but has a low level of blast protection. But then there's a version called the MLPV, which is the mine protected version of the Sandcat. Now, from a distance of about 20 paces, you can barely tell the difference between them. But there's actually a very fundamental difference in the way that the vehicles are built, in the structure of the vehicle. The blast protected vehicle doesn't have chassis rails. It has it uses the blast system as the structural part of the chassis in order to create space underneath the seat and underneath the feet of the occupants, where the chassis rails themselves would have been, or where they are in the regular vehicle. So that it's a fundamentally different approach to how you design the vehicle, even though at a distance of 20 paces you can barely tell them apart.
Moving forward then, or before I go that, one more thing. You raised wonderfully the issue of emergency escapes. And I cannot tell you how many meetings I've sat on where that has been a topic of conversation. And as you've said, if there's a vehicle that's in an incident, it's on its side. Obviously, those vehicles against those doors on the ground can't be open. Trying to push up the other side doors is nigh on impossible. Predominantly, it is either a roof-mounted escape hatch, and there have been some challenging designs that we've been seeing over the last years, primarily because of the amount of effort it takes to open the design. Leave aside your comments, which are valid, as to someone from the outside being able to get into the vehicle in order to rescue the occupants. But I would contend that in a vehicle rollover or a blast incident, and a vehicle's on the side, the effort, or even on straight up, even worse to some extent, the people inside have gone through shock, they may be injured, and their ability to then push out an emergency escape, even with struts on it, is challenging. I see this every time we inspect vehicles. What has become common is then people moving into the rear cargo area and then opening up the rear cargo door and pushing out. That's great at the factory, but if the body of the vehicle has been slightly twisted due to the incident, then it may be that door cannot necessarily be opened very well. Or again, if the vehicle is on its side, there may be some impediment, something stopping that rear cargo door swinging out. Just even a small rock might be in its way. So look, thank you for raising that issue. I'm not sure that there's any great solution to it, but in your experience from the roof-mounted escape hatches, are there any tricks of the trade or any things that you've seen in your days that might be of benefit to the industry?
It comes back again to that whole feature creep thing, because the thing with roof hatches is you need to very carefully define what it's for and not let feature creep turn it into something else. If it is purely an escape hatch, a roof hatch as an escape hatch is pretty much only for an event where the vehicle is on its side. You shouldn't ever have to actually go out through a roof hatch in emergency if the vehicle's still on its wheels. So if the vehicle's on its side and the roof hatch is an escape hatch, there's no real reason for it even to have a hinge and struts or anything like that. It can just be a one-shot release, push-out, fall-out roof hatch, and that's perfectly acceptable as an escape hatch, as a one-shot escape hatch. What often happens is that once you've got that hole in the roof, somebody else comes along and says, well, hold on a second, what happens if I would like to be able to stand up there and to use it to as a shield to return fire? And that's something else completely. That's not an escape hatch, that's a roof hatch for returning fire. And then you need spring struts and spring-loaded hinges, and you need to make sure that it locks in the up position, because if you're standing up there while it's moving, you don't want the thing shutting back on you, and it complicates the product significantly. And I'm very much in favour of an escape hatch being an escape hatch, and it just being a one-shot push-out hatch, which can actually be done quite simply and cheaply, as I say, without bothering to add hinges and struts and springs or anything like that. It just needs to be something that opens and falls out, and you just need to make sure that from the inside it's very, very, very clear that that's what it is, and that nobody tries to open it in any circumstances other than emergency escape. And that's partly labeling and partly training and partly the nature of the handles and everything, just not making it look like a sunroof that you're going to open up to poke your head out of or anything like that.
Indeed. All right. One final question before we wrap up. Just looking forward over the next sort of 3 to 5 years, what do you see as sort of the key challenges in the design of a civilian armoured vehicle?
Hands down, it's electrification. More and more vehicles are becoming electric drive or hybrid drive. They've got significant number of batteries, often lithium batteries, usually under the floor. It's causing a few issues for armored vehicles. One of them is weight, in that the batteries of these hybrid and electric vehicles are adding weight that's come at the expense of payload. So much more effort needs to be put into saving weight out of the armored vehicle. But the other issue is the survivability protection issues of having all those lithium batteries in the car in the first place, in terms of fire, in terms of explosion, in terms of protecting the battery. Now, I'm not one of these people who is electric cars, they all catch fire and they're all very dangerous, because of course we've spent the last 120 years driving around with 60 or 80 litres of petrol underneath the back seat quite happily. Petrol is also an explosive, dangerous material to be carrying around, but it doesn't suffer from quite the same thermal runaway that a lithium battery can. So yes, in an armoured vehicle, we do need to start looking much more carefully at what happens when a single shot enters into that battery and ignites it. What can we do in order to protect the battery in terms of extending the armor protection around the battery, but also containment and fire suppression and all those other issues. When it's a blast vehicle with certainly an underbody blast vehicle with a great big lithium battery underneath the seats, really that's a fundamental design issue. As I was saying earlier, in terms of how you would design a blast vehicle, well, the very last thing you would do was stick a load of lithium ion batteries underneath the seats if you're designing a blast vehicle. So I think everything that's related to electrification, I think there's a lot of issues there. I think we're aware of the issues. I don't think there's quite enough work being done to mitigate them and to be ready for the day where you can't even buy a diesel Toyota Land Cruiser anymore. What happens then? I think there's a lot of work to be done there.
All right, excellent. Look, thank you very much for a wonderful presentation. Again, I think what you've highlighted is that just cutting and welding armored steel and installing ballistic protected glass, etc., into a vehicle is not what it takes to make a dynamic, a vibrant, and effective civilian armoured vehicle. There are design issues at hand, and I think it's incumbent upon all the people in the industry producing the vehicles to understand that holistic approach to design, and for the users, the procurement agencies, the users, the fleet managers, to appreciate that there are these other aspects and to push up through the industry and through the supply chain to ensure that these issues are then met in the most cost-effective and people safety event along the way. So thank you, Nir. Again, we're sorry that you couldn't join us today, and please keep safe up there where you are, and we look forward to speaking with you again in the near future. Thanks again.